of electrons. Reduction is gain of electrons. So we can just figure out who's undergoing oxidation, who's going reduction, undergoing reduction. Can you tell me who's undergoing oxidation? In other words, which of the species is being oxidized? Which one? Chlorine? This chlorine? This chlorine is being oxidized? Well, this one we don't call chlorine. We call that, what's the name of this? Chloride. This one we'd say chlorine in, what was the name of this one again? Chlorate. And so chloride, is chloride losing electrons? Or is it gaining electrons?
Chloride is gaining, but chloride and chlorate is losing.
Okay, so chloride is gaining, and chlorine in chlorate is losing?
Yeah.
Okay. So chloride is undergoing, if it's gaining, then its reduction is gain. So what we say is it's being reduced.
Wait, I got it backward. I think the chloride is on its own is losing an electron.
Chloride is losing
Yeah.
electrons? So if chloride's losing electrons, then chloride is being oxidized. Is that correct? All right. Now the agent is what causes it to happen. So let's say, to use this analogy, let's say let's say you lost your lunch money to some bully. So you're robbed of your lunch money. If you're robbed of your lunch money, are you the robbing agent? Did you rob yourself? No. And so if chloride lost its electrons, who did it lose the electrons to? So chloride was oxidized. If it loses electrons, then what agent caused the oxidation? So normally we think of things like aluminum. Aluminum is easy to oxidize. This aluminum is already oxidized here. Aluminum is easy to oxidize. And what's a good oxidizing? Oxygen. In fact, we live in the oxygen atmosphere. 21% of this atmosphere is oxygen by mole. And so we live in an oxidizing environment. If we live in an oxidizing, does that mean oxygen is oxidized? Or does that mean aluminum is oxidized? Aluminum is oxidized. And so aluminum is oxidized by whom? By the oxidizer. And who's the oxidizer here? The oxygen. The oxygen is the oxidizing agent who's going to oxidize aluminum. And what's going to happen is aluminum is going to lose some electrons. How many electrons can aluminum lose? 3. It's fixed charge. And how many electrons does each oxygen want to gain? 2. And so what are we going to form? What's the formula?
Al2O3.
Al2O3, aluminum oxide. Solid. This is a gas. So we'll balance this 2 aluminums and 3 halves of O2. 3 halves of a mole, 1.5 moles of O2. And so aluminum was oxidized by the oxidizing agent O2. What happened to O2 though? What happened to the oxygens? The oxygens were reduced. So the thing is, when we do this, how do you know? How do you know chloride was oxidized? How can you tell that chloride was oxidized? Or how can you tell it was reduced? How did you determine whether it was oxidized or reduced? And so the first thing we got to do whenever we have a redox and we want to analyze it is to write the... Before I even think about what's oxidized and what's reduced, I'm going to write the oxidation state. So the first thing I do is write the oxidation state, and then I can analyze who loses, who gains. And so whenever we have a question, you know, who's the oxidizer, who's the reducer, I do that unless I can see it straight off. And so let's do the oxidation states here. Chlorine versus oxygen. Who goes first? Not chlorine, oxygen. Oxygen is more electronegative. The more electronegative one goes first, unless it's group 1 or group 2, or hydrogen.
Is that because the three oxygens? Because yesterday
No.
we had something like that. Oxygen went before chlorine, and that's why I was confused.
Oxygen goes before chlorine.
Okay.
Yeah. Chlorine, that means chlorine's oxidation state will be +5. Chloride's oxidation state is -1. Hydrogen versus oxygen, which one goes first? Hydrogen at, and then oxygen at. Cl2, 0. And then hydrogen versus oxygen, hydrogen goes first at +1, and then oxygen, -2. So did anything happen to hydronium? Redox. Redox-wise, nothing happened to hydronium. Do you see that? And so it looks like chloride lost electrons. It went from -1 to 0. In that process, I have this. I have, this is going to be 5 times -1. So 5 times -1 means I'm going to lose a total of 5 electrons. And this is going to be -5 electrons because I'm going to get 5. Actually, I have 6 chlorines here. Do you see that? But I'm just going to look at 5 of these. 5 of the chlorines will be 0. What about that 6 chlorine? What happened to that? Well, here's 5 of the 6. Where's the 6th of the 6? It's over here. When I look at the 6th chlorine here, I have 1 chlorine at +5. And then that's going to go to 1 chlorine at 0. So if I go from +5 to 0, how many electrons must I gain? 5 electrons. So gaining electrons is reduction. So what we say is this. We say that chlorate was reduced, or chlorate underwent reduction. So chlorate was reduced because it gained electrons. But if something gains electrons, it's going to mean that somebody else lost the electrons. So who lost the electrons? These 5 chlorides. This 1 chlorine needs 5 electrons for this particular reaction. And so what that means is those 5 electrons have to come from the chlorides. And since 1 chloride only gives up 1 electron, we need 5 of them. And so the chloride was oxidized. So who did the oxidizing? Who took the electrons from chloride? Oxidation is loss of electrons, so somebody must have took those electrons. What took those electrons is the is the,
chloride and
it was oxidized by who? By what? It was oxidized by the oxidizing agent. Correct? And so that means chlorate was reduced and it's the oxidizing agent. And chlorate reduced, it was reduced by the reducing agent. And so this is the reducing agent. The species that's oxidized is the reducing agent. The species that's reduced is the oxidizing agent. So it's confusing. And so it takes some time. This is something that you don't want to cram like the night before the test. The night before the test is too hard to remember all this, right? It gets all mixed up, and then before the exam, everything's all mixed up in your head, and you end up being confused. And so this is what we have. Chlorate is our oxidizing agent. Our oxidizing agents get reduced. Oxygen here is our oxidizing agent. The oxidizing agent gains electrons because oxygen has an oxidation state of 0. It's an element. Over here, oxygen's oxidation state will be -2. And so the oxygens, each oxygen will gain 2 electrons. It's our oxidizing agent, and in the process, it's reduced. So aluminum here is oxidized, and so we go from 0 here to +3 over here. So each aluminum atom loses 3 electrons. That's oxidized. Who's it oxidized by? It's oxidized by the oxidizing agent. And so this is the reducing agent, and the oxygen's reduced. Does that answer the question? Somewhat?
yeah. Why do we think of, the oxidizing agent as chlorate instead of just the chloride? Because really the oxygen didn't do anything, did it?
The oxygen didn't do anything, but you can't separate them. It's bonded together. And so we take the whole thing as the oxidizing agent. The chlorate is the oxidizing agent, but in reality, only the chlorine gained the electrons in chlorate.
But then it does get separated in the reaction because it moves to the H2O.
The oxygens do.
Yeah.
Yeah. But we don't say chlorine is the oxidizing agent. We could say chlorine in chlorate is the oxidizing agent.
Yeah, like that's what I mean. Shouldn't we say that instead of ever saying chlorate is the oxidizing agent? Or do we?
Yeah, that would be a more detailed picture of what's going on.
Okay.
The chlorine in chlorate is the oxidizing agent. The problem with chlorate is this: the oxygens do have to break off because chlorate has no more room for electrons. If we look at the Lewis structure for chlorate, it looks like this. We can do both the formal charge oxidation state on this one. Let's take a look at the oxidation states first. What's the oxidation state of this oxygen? Not -1. When we do oxidation state, winner takes all. So oxygen versus chlorine, who wins? Oxygen takes all. So it's going to take both of those. So it's going to be 2, 4, 6, 8. And so normally it's 6 valence electrons. Now it has 8 valence electrons, which means it has 2 extra valence electrons, which is going to give it a oxidation state of -2. So the oxidation state of this is -2. These are all the same. So these are -2, -2. What's the oxidation state of chlorine in chlorate? +5. 1, 2. It only has 2 electrons. It loses all these to oxygen. If it has 2 electrons, it's supposed to have 7 valence electrons. It's missing 5 valence electrons, so it's +5. Then we add up all the oxidation states. So -2, -4, -6 plus 5 gives us a net charge of -1. -1. That's chlorate. So it's plus 5. So it's going to want 5 electrons. Is there room for 5 electrons? There's no room because chlorine already has an octet. Do you see that? So I can't just add. Is it possible just to add 5 more electrons? 1, 2, 3, 4, 5. Can I just go ahead and do that? No, it's not going to work. And so what has to happen is the oxygens have to break off as oxide. Is it? If we break off the oxygen as oxide, is that happy? Is oxide stable?
No.
No, and this is why, actually, this is written differently. Some instructors love hydronium. I'm too lazy. I don't usually use hydronium. If I were to write this equation out, this is the way I would have written this equation out. In Chem 1A. In Chem 1B, I use hydronium, pretty much. But in Chem 1A, I just write it like this. Chlorate plus 5 chlorides plus 6 H plus yields 3 chlorines plus, okay, I can get rid of 6 of the 9 waters, so that gives me just 3 waters. So remember, if I have 3 oxygens, how many hydrogens do I need? 6. Because if I have 3 oxygens plus 6 hydrogen ions will make 3 waters. And so when these oxygens break off, they just don't break off. What we need is we need the H plus there to form H2O. And then it will happen. But, you know, we can't just say chlorine because what are you talking about when you say chlorine? You know, there's lots of different chlorines. Normally chlorine looks like this with 7 valence electrons. It's just 1 shy of the octet. And so normally when people think of chlorine, they think of this. But that's not really the case here. The case here is because of the winner take all, you know, and we're using oxidation states to give us insight into this. This is really like this. And so we need to know these oxygens here because that's what's causing it to be like this. This is plus 5 oxidation state. This would be a 0 oxidation state. And so if you were to say chlorine, what we would say is we'd say chlorine Roman numeral 5. The chlorine 5 takes it. You know? That's a big difference because, like, you know, I talked about, what was her name? The chromium 6. Do you know chromium 6? Have you heard? Chromium 6. They made a movie about her. Can't believe I can't remember her name. It'll come back someday. Actually, she was in the news again. You know, she's an environmental activist, and she was out in Palestine, Ohio. They're giving support to people of Palestine, Ohio. Erin Brockovich. Thank you. Erin Brockovich. Have you heard of her? What happened was in the Central Valley of California, there was groundwater contamination with chromium 6. It wasn't chromium 3. Chromium 3 is not as bad as chromium 6. If it was chromium 3, it wouldn't have been so troublesome. And so they call it chromium 6. Chromium 6 is the problem. Well, how do you get chromium 6? You don't get chromium 6 by having a chromium 6 plus cation. That's way, way too unstable. You know how you get chromium 6? You have to stabilize it. And so chromium 6 comes in when we have chromium in the form of CrO4 2 minus. What's the oxidation state of chromium in this? What's this called? CrO4 2 minus? Chromate. So chromate is going to have chromium in the plus 6 because oxygen is minus 2, that's minus 8, plus 6 gives us minus 2. Or chromium 6 is in the form of this one, Cr2O7 2 minus. What's that called, Cr2O7? Dichromate. Dichromate, both of these have chromium 6. So in Erin Brockovich, they just talked about chromium 6. They didn't say, oh, the well was contaminated with chromate and dichromate.
Yeah, so it was from the natural gas pipeline of the Pacific gas and electric company.
Okay, PG&E then.
Yeah.
It was big. They made a Hollywood movie out of it.
Julia Roberts was
Played Aaron Brockovich,
Yeah.
right? Yeah, you know, I've never seen the movie though.
and,
I heard it's good.
Interesting, like, right now there's the Willow Project as well. Like, that's in Alaska where they want to drill for oil. And there's a lot of activists who, obviously are against it because of contamination and everything.
Right. Well, actually, fresh water is so important. Can you imagine if all your groundwater is contaminated with chromium-6 or other things? It's hard to get rid of it. And so, you need to protect water resources. Water. In fact, Las Vegas worked for decades trying to get rid of perchlorate out of their drinking water. You heard that? Perchlorate is very difficult to get rid of because.
Is that a result of fracking?
No.
No. What exactly is it a result of?
It's a result of the perchlorate factory north of Las Vegas. In fact, normally I show a video of the perchlorate factory. It's not just perchlorate that they made. They made ammonium perchlorate at the factory.
Also, it has nothing to do with oil.
No, nothing to do with oil. But perchlorates are very difficult to get rid of out of water, but they were finally pretty successful at it. And so they had a celebration. It's on YouTube, drinking the tap water of Las Vegas. Yeah. And so it'd be something like this. In this case, you wouldn't say chlorine, because if somebody said chlorine, you'd think this, Cl2. And so here, you could say chlorine 5, like we said chromium 6 over there, and then that makes sense. Then that's no problem with that, because then it's an unusual environment, chlorine 5.
And then, so chlorates are oxidizing agent, chlorides are reducing agent. What do we call hydronium spectator?
Spectator. It's not really a spectator, because what kind of reaction is it? Oxide plus H plus. What type of reaction is that? It's you can't just break the oxide off. I'd like to. Let's say if we break the oxide off here, we break that off. We'll form oxide iron. Is oxide iron stable? What do you know about oxide? Oxide is a strong base. Good. Oxide is a strong base. What are the other strong bases? Oxide's one of them. Hydroxide, sulfide, and one more I talked about. Amides. Good. That's good. That was quick.
Superoxides too.
So, yeah, we have those. The superoxides are more for redox properties. And so this oxide, it wants acid. It wants, and so we can help stabilize it. It's a strong base. And so here, each oxide needs 2 H pluses to form H2O. What kind of reaction is this? Strong base plus H plus is what type of reaction? Acid base. So this is a combination of redox and acid base. The hydronium is not really a spectator. It's there. It plays an important role, but its role is acid base, not redox. And so in terms of redox, it's a complete spectator. But in terms of this half reaction, it's important because it forms water. Sometimes we'll have a combination of things to help make it more favorable, because if we didn't have the H plus, then we'd have 3 oxides on the right, and that's not very stable for products, because in driving force we want to go from unstable to stable. And to help stabilize it, we need this H plus. Okay. Anything else?
You know,
Chlorate and are oxidizing and reducing each other.
Chlorate and what?
Chlorate and chloride are oxidizing and reducing each other.
Yeah. So chlorate is, what is chlorate? The oxidizing agent or the reducing agent? Oxidizers, there's other things that help you. Oxidizers are electron poor or electron rich? Electron poor. Reducers are electron rich. So I'd say chlorate is electron poor. Chloride's happy as is, but you know, if there's nothing else, then this is going to be the richest. You know, compared to chlorate, chlorine 5 versus Cl minus, it's going to be different. And so oxidizers are electron poor. Reducers are electron rich, but chloride's pretty stable. So, but there's nothing else, and this is very unstable. So highly unstable, quite stable, but it's got to react because it's easier to oxidize chloride than it is an oxide type thing. Or water.
Chloride reduces so much heat that it gains electrons.
Yeah.
That's what makes a chlorate a oxidizing agent.
Right.
It oxidizes others, but it reduces itself.
Yes, exactly. And so this is what we say is the reduction half reaction. And this is the oxidation half reaction. And so it takes some time for that to click. And so you just keep going over it and over it and over it. And eventually it'll click. Okay, that's in the forward direction. If we were to reverse this reaction, who's the oxidizer and who's the reducer in the reverse direction? And so the thing I ask is, who gets oxidized? Who gets oxidized loses electrons. So who gets oxidized? Yeah, chlorine gets oxidized because we go from 0 to +5. So to go from 0 to +5, we must lose 5 electrons. But who took those? So the oxidizing agent must have taken those. So chlorine got oxidized, but chlorine got oxidized by who? By chlorine? Chlorine got oxidized by chlorine? So anyway, I like say I got my lunch money stolen. Well, who stole it? Well, I stole it. So I stole my lunch money. Does that make sense? It doesn't make sense, but you know what? It's true. In this case, who took the electrons? Chlorine. Who lost electrons? Chlorine. Chlorine took the electrons, chlorine lost electrons, and nothing happened. Or did something happen?
It's because they're different.
Yes, it's because they're different chlorines. This is kind of weird in this sense. How many chlorine atoms do we have here? 6. So who lost? Who lost was one of the 6 lost. And then who gained? All the others. 5 of the 6 gained. So I feel sorry for this one chlorine because these other 5 chlorines just ganged up on this one chlorine, right? Does that make sense? It seems to not make sense because, chlorine versus chlorine, they're equal. But this is what happened. So if we were to reverse this, this is what would happen. One of the chlorines went from 0 to +5. The other 5 chlorines went from 0 to -1. That's going in the reverse. It's not to say the reverse is favorable in this case. Well, but what we want to do is, okay, so one of these chlorines was the reducing agent, and the other 5 chlorines were the oxidizing agent. So this is both the oxidizing agent and the reducing agent. And so it's a little bit weird because it's the same thing. This is called a disproportionation reaction. Disproportionation reaction sometimes happens in redox, where the same species is both the oxidizer and the reducer, but it's not the same atom. Like, for example, this chlorine, if this chlorine is the reducing agent, it cannot be the oxidizing agent as well. They have to be separate atoms. Does that make sense? There are other examples of this. This is a disproportionation reaction, but in the reverse sense, it would be the disproportionation reaction. There are some certain species that are unstable. So for example, mercury 2 plus. Mercury 2 plus, we say disproportionates. Do you know what happens with mercury 2 plus isn't so stable? So what some mercury 2 plus salts do is they disproportionate into mercury 1. In that process, they're gaining electrons, but who are they gaining electrons from? They're gaining electrons from mercury. So this just disproportionates into, actually mercury 1, sorry. Mercury 1, I should say, disproportionates into mercury 2 plus mercury metal, liquid mercury. I screwed it up this morning. So this is a disproportionation where, actually, let me change this. I have 2 mercuries here. One of the mercuries gains and the other mercury loses. Okay, so disproportionation. And so that's what's going on here. And so this is why it's kind of weird. And then we compare which one's a stronger oxidizer, chlorate or chlorine. It turns out that chlorate is a stronger oxidizer than chlorine. Look at the oxidation states. So this is stronger, this is weaker. Also, this is skeleton redox, so we already know there's got to be a driving force. And that means chloride is a better reducing agent than chlorine, which is going to be a weaker reducing agent. So we're going from stronger to weaker. So this is a bit confusing. Okay, now to confuse you a little bit more, these are the oxidation states. Oxidation states are critical for analyzing redox reactions. So this is the first thing I look at when we do redox reactions. I think about what are the oxidation states. For acid-base reactions, I don't do oxidation states. Usually. Sometimes I'll do it, but most of the time for oxidation states, you know what I look at? First I look for formal charge. And so what are the formal charges? Now, oxidation state, winner takes all. Formal charge is sharing, equal sharing. And so what is the formal charge on this oxygen here? -1. We don't usually write the 1 for formal charges. And all these oxygens are the same. So all these oxygens have minus formal charge. Now, we never get these confused because we never compare apples to oranges. If we're doing redox, then we're going to stick with the green. If we're doing acid-base, then we'll look at the red. Does that make sense? But we never compare, like, how can it be -2 and -1 at the same time? Well, it's neither of those, somewhere in between. Oh, actually, no. If it has a negative formal charge, it is negative, at least. And then it might get a little bit more charge density from chlorine. Okay, what's the formal charge on chlorine? +2 is correct. And so those are fairly high formal charges as far as formal charges go. The formal charges add up to the net charge. So +2 -1 -1 -1 gives us -1. So we can either sum the formal charges to get the net charge, or we could sum the oxidation states and that would give us the net charge. Both of them are useful or giving us insight into how these species behave. All right, let's take a look at the next reaction here. On the pre-lab. The next reaction is CaCO3 solid. CaCO3 solid is called plus SO3 gas. Which is called sulfur trioxide. And this is going to go to CaSO4 solid and CO2 gas. So CaSO4 is calcium sulfate. All right, who's the oxidizer, who's the reducer? If we want to know who the oxidizer, the oxidizing agent is, and who the reducer is, or the reducing agent, then the first step is to do what? Look at the oxidation state. We do oxidation states for redox reaction, so let's go ahead and get those. Calcium, carbon, or oxygen, which one goes first? It turns out group 1 and group 2 go first, because those are fixed charges. Calcium is only going to have one charge on it in compound, +2. And then carbon versus oxygen, we take more electronegative oxygen first. And so we go -2, it's preferred charge, and that leaves carbon at +4. Carbon. Sulfur versus oxygen. Oxygen's more electronegative, therefore it's going to get its preferred charge of -2, which leaves sulfur at +6. Calcium, sulfur, oxygen. Which one goes first?
Calcium.
Calcium at +2, and then oxygen at -2, which means sulfur is +6. Carbon versus oxygen. Oxygen at -2, and that leaves carbon at +4 and CO2. All right, so who's the oxidizer? Who's the reducer? Which one's the OA? Which one's the RA?
They all stink.
Yeah, they all stay the same. They all stay the same, which means this is not redox. Redox reactions are electron transfer. Well, if it's not redox, then what kind? There's no transfer of electrons. This is not redox. If it's not redox, then that must mean it's a metathesis. Is this a metathesis reaction? Does it look like a metathesis to you? No. Single replacements redox. All single replacements will have a change in oxidation state. So this is not metathesis, which means it must be acid-base. But do you see any acids there? No, because acids begin with H. Do you see any bases? Maybe. But, you know, that's only one type. This is not a Bronsted acid-base. For Bronsted acid-base, we need a proton donor and a proton acceptor. We don't have any hydrogens here. Now, the protons, the nucleus is not going to lose the protons, otherwise it would be a nuclear reaction and not a chemical reaction. So this is not a Bronsted acid-base, which means it must be a Lewis. And in fact, that's what it is. This is a Lewis acid-base reaction. Now, to analyze Lewis acid-base reactions are a bit more complicated. Right? Bronsted acid-base reaction is a lot easier, proton donor, proton acceptor, but Lewis are more difficult. And so I was fearing we'll do 2 quizzes today about that. But the 2 quizzes are going to have a different set of rules. This first quiz we're going to have, you could, it's open book, open notes, and you can work with your neighbor if you want. The second quiz we're having today, you guys know what the second quiz is? Nomenclature. That one's going to be closed book, closed notes. And you can't work with your neighbor on that one. You have to just do that from memory.
Can I ask if it includes carbon in the picture? Or if it,
What is the nomenclature quiz? Does anybody already know what's going to be on it? From the exam. Not the bonus ones, just the regular ones. All right, so this quiz, we're going to do this. Not sure if I missed stuff on the recording. So we're looking at the worksheet now. Gas formation, one. Stronger, most of the time you'd be correct in saying H2O is the weaker acid, but not in this case. Do you know what the weaker acid is? The weaker acid is CO2. This is the weaker acid. But how can that be an acid? There's no H to donate. Acids are proton donors, aren't they? Hydrogen donors. There's no hydrogen for CO2 to donate. Do you see that? So how can that be an acid? Yeah, this is not a Bronsted acid. This is a Lewis acid. And that's the reason why. If you wanted to do Bronsted acid, then we could go stronger acid, sulfuric acid, to weaker acid, carbonic acid. But carbonic acid decomposes into water and CO2. It's the CO2 that's the acid part of this. And CO2 is a pretty decent Lewis acid. CO2 is a pretty decent Lewis acid, and we see it in different places. So, for example, in your titration, how long did the pink color have to last? 15 seconds. Why? Because there's CO2 in this room. And the CO2 in this room is acid, and what that does is it goes in and neutralizes some of the base in your phenolphthalein mixture. And what that's going to do is it's going to convert it back to colorless. You can do this rapidly. So for example, if you were to exhale on your solution, like you're exhaling CO2, then it's going to change color more rapidly. So for example, if you got a straw and then just started blowing CO2 bubbles in your titration mixture, it'll last 1 second, the color will disappear right away. The other place we see it is each time we exhale, we're maintaining pH balance. Do you know your blood has to be slightly basic? Slightly basic is going to be a higher pH or a lower pH than 7. It's going to be slightly higher. And what can happen is if you don't get rid of the CO2 efficiently, then that can lower your blood pH. And if your blood pH gets too low, it results in a condition called acidosis. Have you heard of acidosis? Your blood pH is too low. And so we see CO2 as an acid in other things as well.
That reminds me, you talked about bases. No, was it bases or acids that break the scale? Like the most acidic.
Oh, yeah. Right. Because normally when people think about the pH scale, they think from 0 to 14. Is that correct? The pH ranges from 0 to 14. True or false? False, right? pH scale is a little bit wider than 0 to 14. And so what is the lowest pH possible? That's what I was asking. What is the lowest pH? Well, I don't know. What's the lowest pH that's been measured in natural waters? This is kind of interesting. You know, the lowest pH to have been measured in natural waters. Well, this is not really natural, you know, but it was in California, and it was in a mine in California, and so that was the lowest pH. I think the pH was negative 2 point something, 2.4.
I'm sorry, that is-
But it was because it was contaminated water. Yeah. What was the highest pH to be measured? That kind of stuff. So that's what I was when we were talking about pH in Chem 4. Okay, so this is the CE. What did you get for the IE?
The solids don't change.
Yeah, solids don't change. What about H2SO4?
Partially dissociates to H.
Partially dissociates. Good. To what?
H plus HSO.
So when you put H2SO4 in water, water can pluck off the first proton, but it struggles to pluck off the second proton. This is in water. Carbonate has no problem plucking the second proton off, but water does. And so what we're looking at is the species in water here. Okay, calcium sulfate, solid. H2O,
Stays the same.
and CO2. So this would be the ionic equation, and then we would have the net ionic equation. And what would the net ionic equation be? Are there any spectators? No. So they're the same. All right. What's meant? Okay, did you guys get that? Question?
So, plus H2O4.
Yes.
2H plus and SO4.
That's the most common error. 2H plus and SO4 2 minus. Is it supposed to be that? No, it's not, but lots of people do this. About maybe 30% of the class will write this here, and then I'll circle it and deduct points. Basically, why? Why am I going to deduct points? I mean, from this. Yeah, H2SO4 is a strong acid. Strong acids are strong electrolytes. Strong electrolytes dissociate. But what do they dissociate into? And it boils down to this. The hydrogens on H2SO4 break off one at a time. So if you're water, and how was that quiz? Was that quiz pretty easy?
Well, if we took it now, it would have been easy.
It would have been?
Yeah. Because I just figured it out now.
Yeah, well, I was hoping that quiz was going to be easy. But we'll see. Anyway, so we have H2SO4 like this. There's some formal charges on this. I'm not going to write them out. What do you think? Do you think two waters coordinate the attack? So, you know, all Bronsted acids are also Lewis acids, and all Bronsted bases are also Lewis bases. So I'm going to do this as a Lewis rather than a Bronsted. In terms of Lewis, remember Lewis bases are electron pair. Lewis bases are electron pair. Lewis acids are electron pair acceptors. So in all Lewis acid base, we always follow the electron pair. And so it's always the base attacks the acid. So in this case, the base is going to pluck this proton off. And it's going to pluck this proton off. Do you think they're going to coordinate it so that they pluck off the proton same time? 3, 2, 1, 0, pluck the protons off. Do you think that the two waters coordinated like that, or do you think they get plucked one at a time? One at a time. It depends. It's random. So let's say this one gets plucked off. And we form hydronium, or H+. What do we call that? H+. And bisulfate. So now we have hydronium and bisulfate. Actually, these also have a negative charge, and this is +2 here. Just to keep the charges, okay? Do you think after the first one's gone, do you think the second one is going to be just as easy as the first one, or more difficult, or easier? Do you think, okay, now the first water plucked this hydrogen off. It was easy. Why was it easy? It was easy because sulfuric acid is a strong acid. Strong acids lose they're excellent proton donors, right? Now, do you think the second water is going to have as easy of a time as the first water? Not at all. Not at all, because this is not sulfuric acid. What is this? This is bisulfate, and bisulfate is not a strong acid. It's a weak acid. And we only ionize the strong because the weak only partially ionize. And so this is going to be a lot more of a struggle because, the net charge on this is -1. Before, the net charge was 0. And so now we're trying to pluck off something that is going to have a stronger hold on the proton. And so to remove the second one is much more difficult than the first one. And so water can't do this. This is just looking at a beaker of sulfuric acid. What are the major species in a beaker of sulfuric acid? The major species are H+, or hydronium, and HSO4-. It's not this. And so we're trying to be a little bit more accurate, although H+ should have been hydronium, but we're not going to deal with that. And so we don't write this, we write this here. Now in the redox chart, you'll see that we have a sulfate in the redox. Remember this? In the redox chart, it was written separate. But the reason it was written separate is because in redox, you might take sodium sulfate and mix it with HCl. If you take sodium sulfate and mix it with HCl, it's going to come out something like that. So, yeah, this is getting a start on things here, so that's good. There are a few more things I wanted to say about this. Not all these reactions are redox. Like, for example, number 1 was redox, number 1 was not redox. What was this reaction called? What type of reaction was number 1? Number 1 was a double replacement or metathesis reaction. Number 2 is also going to be a double replacement or metathesis reaction. Number 3 is also going to be a metathesis or double replacement reaction. Did anybody do number 3? No? Okay. I'll just wait for that. How much time do you guys need to do the... Actually, all of you just have one more reaction to go, or do you have multiple reactions to go for experiment 18? Just the last 2? All right. Then this is what we're going to do. I guess I'll have to talk about some of this tomorrow in class. So what we'll do today is I want to give the nomenclature quiz. Nomenclature quiz is just going to be closed notebook, and you aren't allowed to collaborate with the neighbor with this. And then after the nomenclature quiz, then go ahead and get started on the lab. Okay. at least get set up. You know, you need the hot water bath. Somebody left their beakers on the hot plate last time. So try not to forget your stuff. If you're done with the lab, then that's it. You can just work on the worksheet at home or here, and then we'll see you tomorrow. This is a bonus quiz here. Thanks.